Hi, this is a brief introduction to our paper, A Geometric Algorithm for Robust Multibody Inertial Parameter Identification, to appear in Robotics and Automation Letters. Identifying the inertial parameters of a robot, or for that matter any multibody system, is a prerequisite to any dynamic model-based planning and control method. Because the inertial parameters appear linearly in the dynamic equations, inertial parameter identification is most often formulated as regularized linear least squares problem. In practice, however, identifying a robust inertial parameters is a highly challenging problem, sensitive to noise and initial conditions, and also dependent on the reference trajectories used. In many cases, regularized linear least squares methods are not very successful at accurately identifying a robot's inertial parameters, especially for robots with many degrees of freedom and subject to noisy and insufficient measurements. In this paper, we argue that regularization of an ill-posed least square error criterion with the use of standard Euclidean metric is a primary culprit. So rather than using a standard Euclidean metric, we propose a more natural distance metric for inertial parameter identification, defined by a reference frame invariant Riemannian metric on the space of 4x4 symmetric positive definite matrices. The proposed Riemannian metric is also invariant to the choice of physical units and scales used in the characterization of masses and inertia tensors. And these invariant properties essentially allow a well-conditioned identification of a physically consistent inertial parameters. Based on this geometric setting, we formulate the inertial parameter identification problem as minimizing a certain geodesic distance-based nonlinear least squares criterion on the manifold of symmetric positive definite matrices. And we also derive a corresponding geometric optimization algorithm for this problem. And here are some identification results for experiments on a human subject. The identified parameters of each of the links are visualized as equivalent uniform ellipsoids. The least squares-based solution using the standard Euclidean metric is shown to result in considerable errors, with many of the links estimated as point masses or flat in one or more dimensions. In contrast, the identified parameters from our method are much more physically plausible. For further details, please visit us at the poster session. Thank you.